My name is Hamza Fawzi, and I work in the Department of Applied Mathematics and Theoretical Physics, and I'm affiliated with the Cantab Capital Institute on Mathematics of Information. My area of mathematics is called mathematical optimization. Okay, so it's really an area at the intersection of many different areas of mathematics, but also computer science and engineering and operations research also. The main problem here is to solve optimization problems that are defined mathematically, and to design efficient algorithms to be able to solve these optimization problems. So it can go from very applied to very, very theoretical. So you can be on the applied side where you work with real world optimization problems and you try to find efficient algorithms for them, to solve these practical problems. And you can be on the more theoretical side where you study the geometry of optimization problems and so on. And this is probably where I am more. I fit a bit more in the theoretical aspects of optimization, in studying and understanding the fundamental aspects of these optimization problems. In the applied side, there are many different applications of optimization. It's used in virtually in really all areas of engineering, of operations research, in supply chain, and in statistics, in even, I don't know, in quantum information theory. Here in this building, we have people doing quantum information theory. They use tools from optimization. In power networks, so if say you're a utility company, electric utility company, you have to decide each day how much power to generate at the different power plants. And so there is a certain optimization problem that you need to solve. And this is a real world application of optimization, and this in general is a difficult optimization problems, and so there has been a lot of research in trying to understand the geometry of this optimization problem and how to design more efficient algorithms for it. I did my undergraduate studies in France, in Paris, and then I moved to the US for graduate studies. I spent about a year and a half at UCLA in Los Angeles, and then I spent 4 years where I did my PhD at MIT in Boston. My area of research was exactly on this, on understanding a bit more, understanding the geometry of certain classes of optimization problems called semi-definite optimization problems. So these constitute a class of optimization problems that we can solve efficiently, and that generalize a very well-known class of optimization problems called linear programming, are more complicated because in a sense they have non-linearity in them. Okay, even though they are still efficiently solvable, they are still non-linear optimization problems, and so one needs new tools to study these problems compared to linear programming, which is has been well studied in the past 50 years or so. And what I try to do is to try to understand the fundamental aspects of semi-definite optimization problems, both the algebraic aspects as well as the geometric aspects. I've just graduated from my PhD less than a year ago now, and so I'm still naturally, there are still a lot of questions that have been left open after my PhD thesis, and I'm naturally continuing to try to understand these questions a little bit. They have to do with convex sets defined using polynomial equations and inequalities. In general, these are non-linear sets. They are non-polyhedral sets, and the properties of these convex sets are much less well understood than polyhedral or polytopes, which are the sets that we study when we do linear programming. And so a lot of my work has to do with understanding these sets, understanding very basic geometric properties of these sets. Some of my recent work has been motivated by problems coming from quantum information theory, optimization problems coming from quantum information theory, and how one can formulate them using semi-definite optimization. One of the things that I really enjoy a lot in being in this institute are really the students. So it's really to be able to. So we have these weekly coffee hours where I have the chance to talk to students, get to learn about what they do. Even if I'm not really advising any student in this year, but get to know what they do. This institute is at the intersection between DAMT and DPMMS, so this also brings together a little bit the two departments. Especially the area that I work tends to have interactions with people outside of optimization. As I said, optimization is used in statistics, and so that what leads me a little bit to talk to people in statistics from time to time. Since I arrived here, which is less than a year ago, I have talked to people in different areas. I've talked to people in quantum information, for example, which are really sitting next door here. But I have also talked to people doing statistics and doing more statistics and biology and so on. So it's really a great place to be able to talk to many different areas, which I think is really nice.